Welcome to Pomodoro Joe for Saturday, April 29th, 2023. Today we're doing LeetCode problem 1697, checking existence of edge length limit. 1697, checking existence of edge length limited paths. This is a hard problem. This one's a really hard problem. All right. An undirected graph of n nodes is defined by edgeList, where edgeList index I is equal to u, v, and dist. Denotes an edge between nodes u and v with a distance of dist. Note that there may be multiple edges between two nodes. For example, here they have two edges, one of distance 2 and one of distance 16 between 1 and 0. Given an array queries where queries index I is equal to p, q, and limit, your task is to determine for each query whether there is a path between p and q such that each edge on the path has a distance strictly less than limit. Return a Boolean array answer where answer length and query length are the same, and the jth value of answer is true if there's a path for queries j that is true and false otherwise. Oh man, this one is tough, and I do not have a lot of time today. So we'll put 25 minutes on the Pomodoro timer, and I am going to zoom through this. I won't be explaining a lot, and maybe I'll come back later and do some voiceover to explain it. Right, for this one, we're doing a union find. So the idea here is we will sort all of our edges by length. Then we will actually build our subgraphs. We will create a bunch of subgraphs by the length of the edge in the edge list. So for example, if we have a query that's looking for anything with a limit of up to length 20, then we want only edges in our graph that have length 19 or below, or something less than 20 or below. So essentially we'll build these graphs that actually meet the limits of our query. So we'll probably be sorting our queries by limit. So we'll do the smaller graphs first, building up to the larger graphs. Then we'll build these smaller graphs out of edges that just fit our limit in our query. And then we can check to see if the two nodes that we're looking for are also in that graph. Now we also need to make sure that they're not just in the graph, but they're in the same graph. So for that, we'll be using a union find. Union find is a more advanced data structure or algorithm. I'll try to explain it, but again, I have very little time today, so I'll probably just be coding. All right, here we go. Let's start by creating our union find class. Now for this one, I will also be doing an optimization right off the bat because I know I need it. So this mapping will just keep track of which nodes belong to which subgraphs. Okay, so this is our union find data structure. It has three methods: the init, it has the find, and it has the union. So find will find the subgraph. In this case, in the generic case, it's called the parent. In our case, it's a subgraph. So it'll find the subgraph that this node is in, and union will actually take two subgraphs and merge them together into one. Okay, first thing we want to do is sort our edges. We're going to sort by distance. So that is element number 2 in our edge list, or in each element of the edge list. So it'll be node A, node B, and then distance between them. So that's going to be x at index 2. Next thing we want to do is sort our queries. But before we sort our queries, we need to keep track of the original index of the query. So for that, we'll have a mapping. But this Q, we will have to make a tuple. Okay, so this is storing the index for a given query. That way, when we run the query and we create our result, our answer, we'll know which index to put the result into. We're going to be doing all of our sorting by distance. And again, with the query, it's going to be node 1, node 2, and then the distance. That's going to be x at index 2. So we've sorted our edges, we've sorted our queries. Now we need to create our subgraphs, and we need to create our initial empty, or our initial result, I guess I should say. I should call this current edge index. We're just going to assume true for the time being. At the end, we will return our result. But now we have to go through and actually run all of these queries. All right, so let's do that. Okay, so our query, we're going to have a node 1, a node 2, and some distance d. Now we need to add all of our edges to our current union find. So we're going to go through and add edges, but only edges up to the limit of this query. So instead of d, maybe I should call this limit. Maybe this name is too long, so we'll just call this current edge instead of current edge index. So the current edge, so we're going to get our current edge out of the sorted edges list, and we want to find its distance, so that's going to be at index 2. So while that is less than our current limit, then this is a valid edge to put in our current graph. All right, so now we have node 1, node 2, and now we need to actually add this edge to our union find to keep track of. So let's see, I'm actually going to change these names. Instead of N1, I'll call it query 1, query 2. Those are the query nodes. So this edge is going to have an N1 and N2 and some distance D. That's going to be the sorted edges. Okay, now we just need to add this to our subgraphs. Not index 2, that's right. So we'll just union these two nodes together. And we don't actually need the distance in this case. And then we need to move on to the next edge. So this is building up a subgraph using only edges that are below our current limit. Okay. Once we've built up that graph, now we'll actually execute our query, and that's going to be a little bit simpler. So first we need to figure out what's the reverse index, so like the proper index to put our query back into. Let's see, that's going to be in this index map here. And again, we need to create a tuple out of our query. All right. And then our result at this query index. That's just going to equal whether or not these two query nodes, so that's Q1 and Q2 here, if they're in the same subgraph. So we can do that by checking the subgraph, find Q1, and if that's the same as the subgraph that we find for Q2, then they are in the same subgraph and all the edges in that graph are below our limit, so that'll be true. Otherwise, it will set it to false. Okay, barring any typos, I think this should do it. Let's give it a shot. And of course, I have typos. Let's see what's going on here. It's a bad indent. Right. No, that's not right. This is the bad indent. Current edge is not defined because I have too many R's here, which means I copied and pasted here. All right, see if that works. Subgraphs plural. And that works. Let's see if we can pass all the tests. So again, this one's super complicated and I really don't have enough time to give it the time that it deserves. All right, and we do pass. And we do okay, 52% for runtime, 7% for memory. Yeah, so this one, super tricky. I will try to make a better video on this later, but today, that is all for me. All right, hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.